Okay, I'll leave now.
Okay, so should I start?
No,
I copy the
think that
video.
first we have to share the link.
Yes,
in
yes.
Discord, and maybe I will make an introduction and share it.
Yes.
Your CV is quite long. Bueno, no sé, parece que empecemos, Cristian, o dejamos unos minutos, no sé si.
Yo dejaría 1 o 2 minutitos. Creo que alguien preguntó algo también. No.
Bueno, no sé si ya empezamos.
Yeah, I think we can start, yes.
Bueno, pero empiezo en español. Hola, les damos la bienvenida al curso M2 de la 34ª edición de la ECI, la Escuela de Ciencias Informáticas. Como saben, este curso es sobre Introducción a la Teoría Homotópica de Tipos, va a estar dictado por Pierre-Louis Curien. Tengan en cuenta que las consultas que ustedes quieran hacer las vamos a leer por el canal de Discord, que deben ya estar conectados. Y que tengan en cuenta que hay una demora de alrededor de unos 20 segundos entre que ustedes, entre que se dicta el contenido de la charla, digamos, y ustedes lo pueden ver, así que cuando ustedes hagan una pregunta es posible que esa pregunta esté 20 segundos atrasada con respecto al momento en que se emitió ese contenido. Bueno, creo que voy a pasar a hablar en inglés ahora. Let me introduce you to Pierre-Louis Curien. Pierre-Louis, please correct me if I make any mistake. So Pierre-Louis is currently Emeritus Director of Research at CNRS, which is the French research center. He graduated from the École Normale Supérieure with a degree in mathematics. In 1979, he obtained his doctoral degree at the University of Paris 7 on sequential algorithms and concrete data structures under the supervision of Maurice Nivat. And in 1983, he obtained his habilitation thesis on categorical combinators, sequential algorithms, and functional programming at the University of Paris 7. For more than 40 years, he has been a professor and researcher at various institutions, including the École Normale Supérieure and the University of Paris 7. His main topics of research include the lambda calculus, rewriting theory, type theory, proof theory, and category theory. And he has made important contributions in topics such as explicit substitutions, linear logic, Curry-Howard for classical logic, operats, and homotopy type theory. Pierre-Louis has published, I believe, one book on semantics with Roberto Amadio. He has published many articles in renowned international conferences and journals. He has also taken part in editorial boards of specialized journals, in committees of 20 international conferences, and as the organizer of many scientific events. He has supervised 18 PhD theses. I think one is currently ongoing, and he has been a member of the jury of more than 100 PhD and habilitation theses. Pierre-Louis has also coordinated and participated in international research projects, and he has coordinated many research grants from the French government. He has held positions in management in research institutions. Among them, he was the founder and head of the Proofs, Programs and Systems Laboratory at the University of Paris 7. He was the founder and head of the research team PR², which is centered in proof theory and specifically development of the TOC proof assistant. And he was also a member of scientific councils and scientific director at the French Ministry of Research. Well, Pierre-Louis has received awards, and in particular last year in 2020, he has been awarded with the Grand Prize of the INRIA French Academy of Sciences Grand Prize, which is the most important award that the French government gives to computer science researchers. So I think that without any further introductions, I welcome you all again to the course, and I shall give the word to Pierre-Louis.
Okay, so thank you, Pablo, for this flattery introduction. And so let me start this course. So it's a course on homotopy type theory, which means that before all, it's a course on type theory. So probably during the first hour and probably a little bit more, we will speak mostly of type theory, and homotopy type theory will come gradually and will become prominent from tomorrow. Okay, so first of all, most of my notes are written in the form of slides, and we will have the slides after each day, the slides of the day. And these slides themselves are built upon mainly two sources. So one is a canonical source for homotopy type theory. It's called the Hot Book. And this is a very, very nice collective book that was produced during a special year devoted to this topic at the Institute of Advanced Study in Princeton in 2013, I believe. And this book is available freely because it has been meant to be free of access. And also for some advanced topics toward the end of the course, I will rely on excellent notes of a PhD student in our laboratory called Hugo Munclay, and his lecture notes are available, and you have the links here. Okay, and again, you will have these slides. Okay, so let's first do a very little bit of history. The origins of type theory go back to the time of paradoxes, and paradoxes the time of paradoxes was let's say the beginning of the 20th century, when formal logic started to emerge, and the first tries in making mathematical logic formal hit on paradoxes. So probably the most well-known paradox is that of the set of all sets that do not belong to themselves. So, okay, so you have this nice little formula here. And this formula here is contradictory, because if I give a name to this set, so I suppose that this guy is a set. So it has, let me call it B, okay? So this set, suppose that it belongs to itself. In this case, it is not satisfying this predicate. Hence, it is not in B. So you see that B belongs to B implies that B does not belong to B, and this is a contradiction. So how was this problem overcome? By introducing a notion of type. And this is a philosopher and mathematician, Bertrand Russell, who proposed the first time a notion of type theory, where he advocated that you cannot write such things. They are too dangerous. What you can write are sets, so definitions where you say the set of A belonging to some types. What is blue here? Such that blah, blah, such that some property holds. And with this caveat, with this more cautious way of forming sets, okay, and this is called forming sets by comprehension. So the comprehension is this thing here, that some property holds. So this is called comprehension. So a set defined by comprehension inside some type A is okay. Okay, so we need to have a notion of type. So Russell can be probably credited for the idea of types. And of course, modern programming languages do not refer to these old time paradoxes, because the notion of type is so natural that you don't need to go back in history to justify it. Okay, so you know that you program with numbers, or you program with functions, or you program with lists, and all these are quite different types. Okay, so types are also independently, so to say, present in programming languages. Okay, so what is type theory? The contemporary type theory, what does it look like? Well, it's a kind of common heritage of Russell, and then of a very important other logician called Church, who is the inventor of the lambda calculus, among other things, but also the inventor of the Church thesis about different models of computation that are all equivalent. And finally, Per Martinlöf, who introduced the notion of dependent type theory, okay, which is the main subject of the course here. And just to give you some pointers in history, Martinlöf type theory started in the early 1970s. So it's now more than 50 years old. Okay, so now homotopy type theory is much younger. It's something that is definitely a part of this millennium. Okay, so it started in the mid 2000s, and it became very active, let's say, after 2010, and even more active after 2013, this famous year, special year which I mentioned. And the addition provided by the sort of founder of this homotopy type theory is Vladimir Voevodsky, a famous mathematician who is not in foundation in computer science, but in algebraic geometry. And but he was interested in foundations, and he proposed homotopy type theory, which we will discuss in this course. Okay, so far for the historical pointers. And as I told you, types are best introduced, especially towards a computer science audience, in the language of programming. Okay, so let me give you rapidly some very simple types. So this should be known to everybody in the audience. Nat is a type, the type of natural numbers, and for example, 3 is an element of that type. And in type theory, you write 3 column NAT. And now you have NAT times NAT, which is the type of pairs of numbers, of natural numbers. For example, the pair 3, 4 is an element of this type. Then you have the type NAT arrow NAT, which is the type of functions from natural numbers to natural numbers. And as an example, if you take the function that doubles its argument, so it maps x to 2x, this is an element of this type. And it can be written in different ways. So in usual mathematical texts, you will often find this notation. So x is mapped to 2 times x. But in lambda calculus, we want to have a notation for the program, and Church introduced this lambda notation, which gave its name to lambda calculus. So lambda x dot 2 times x is a name. It is a way to describe this function formally. And then what can you do with functions? You can apply them to arguments. Okay, so you can apply this double function to 7, and then, well, the result is 14. And if we want to see exactly what happens, we can do this a bit more slowly. So applying this function will mean first to replace the argument of the function, to replace the formal argument of the function by the actual argument of the function in the body of the function. So this is the body of the function, and we substitute x for 7 in this body so that we get this formal expression. And then the rest, okay, this is multiplication, and this is something that you learn in primary school, but it is not the important thing here. What is important thing, what is conceptually important is this first step, replacing the formal argument by the actual argument. Okay, so now a word about lambda calculus. So I'm not sure that everybody in the audience had a real introduction to functional programming and to lambda calculus. So I will at least recall some basics here. Okay, so the lambda calculus is an extremely concise kind of a very, very pure and concise programming language, where programs are of 3 kinds. And so this is a syntax for all the programs that you can write in the lambda calculus. So this is lambda calculus without additional features, without types. It's something sometimes called pure lambda calculus or untyped lambda calculus. And so a lambda term can be either a variable or a term applied to another term. So here you have to think as this term here applied to this term here. And application is just denoted by juxtaposition. And then in the middle, you have lambda abstraction, which is corresponds to procedure declaration in most programming languages. When you say, well, I declare this function with parameter x, and this is the body of the declaration. And so here you have the functions, function application, and variables. And there is a computation rule that allows you to transform lambda terms into other ones. For example, to get this sort of thing, like in previous slide. And this reduction is again very, very simple. It's called the beta reduction, and it says that if you apply a lambda abstraction to some term, you can reduce this application to the body M in which x has been replaced by n. Okay, and as a matter of fact, replacing x by n is something very intuitive, but a little bit tricky. Okay, so again, many of you are probably familiar with this little tricky point, which is called the static binding. But let me introduce it here briefly. Suppose that I have a term m, okay, which is lambda x, lambda y, x plus y. So this term describes addition. Okay, it takes two arguments, x and y, and returns x plus y. Okay, now if I apply this term to y and x in this order, what I expect is to make the addition of y and x, because okay, this is the addition. This says m should add the second argument to the first argument. So here, the second argument is x, the first argument is y, so the result should be y plus x. Now, if we do this uncarefully, something strange will happen, because if I rewrite my, if I do the rewriting of my, if I do apply beta reduction to my, okay, and if I do blindly what I said here, I will replace x, okay. What is the body of m? The body of m is this term here. And in this term, I will replace x with y, okay. So that gives me lambda y, y plus y. And you see that I use colors to show you the different kinds of y's, because the blue y was there before somehow, and the red y comes from outside. It comes from the application of m to y. And this is not what we want, because if that would be the correct thing, then applying this to x again would give me, replacing y by x, would give me x plus x and not y plus x, which I wanted. So the idea, the problem here is that this guy y was a free variable in this term, but after substitution, this y has become captured by this binding here. Okay, so lambda x is called the binding operator, and we should avoid this capture of free variables becoming bound variables. A variable that is under the scope of a lambda is called bound. Okay, so what should we do? What one should be careful when defining this reduction, that to make sure that before we apply lambda x to m, we should possibly rename the variable x here, so as to avoid any such problems. And this is exactly what we do here. We can rename this x into z, some z. Okay, so then your m is now lambda z, lambda y, z plus y. And then everything is okay, because if you apply this m with lambda z instead of lambda x, okay, you apply it to y, then you get lambda z, y plus z, okay, and the y is not captured. That's the point. The red y, which was here, okay, and which is here, is not captured. So then I can apply x, and the x will only replace the z, and we will find y plus x. Okay, so this is, we will not do computations real computations in the course. This is just to give you some background and to explain you that even if lambda calculus is extremely simple, the most basic definition in the lambda calculus is beta reduction needs a little bit of care. Okay, good. And yes, as a matter of fact, if you look at historical books on the lambda calculus, almost no book gave a correct definition of beta reduction. So the correct definition of beta reductions were given much later by people doing computer science, essentially. Okay, so now I will discuss a little bit more the lambda calculus to explain you that also the lambda calculus hides some kinds of paradoxes. Okay, it's not paradox, but it's wild. It's a bit strange. Okay, if it is without types. So in the lambda calculus, you can do something which may look a bit strange. You can really apply a term to itself. Nothing prevents you to apply, for example, variable x to variable x. So you have xx. And then nothing prevents you to form lambda x, xx. And then nothing prevents you to add delta, this term here, to itself. This is delta delta. Now, you can observe that delta delta reduces to itself, delta delta. Why? Because, well, delta is lambda xx, lambda xxx. You replace x by delta, so you see that xx becomes, after substitution, delta delta. So you see that from this term, you start an endless loop of computation. Delta delta reduces forever to itself. So in particular, it doesn't produce any interesting value. And of course, this is not what you expect most of the time. You expect that a program, even if a program is not going to terminate, okay, so think of, for example, a program that produces all prime numbers. Okay, this can run forever, but nevertheless, it produces results. Okay, an infinite list of results, but it produces something, and somehow this is something that we want to avoid, to have programs that do not produce any interesting effect or value. And again, how did Church solve this this problem? By introducing types. So types again here were used to discard such terms. So in fact, in the simply typed lambda calculus, you cannot type xx. So you cannot type delta either, and you cannot type delta delta. In more sophisticated type systems, you can type xx because for example, you could have a type system which allows you to give several types or even an infinite number of types to some terms, to some variable. So x could have the type A arrow B and the type A, okay, and then xx is typed, okay, of type B, and then we could even type lambda xxx. But as a matter of fact, no decent type system will ever type delta delta for one very important meta reason, which is that well-typed terms in some type system always terminate. So usually when you introduce a type system, it's one property that you want to guarantee, that the type system will guarantee termination of the programs. So that in a type system that guarantees termination, a term like delta delta cannot be typed. Okay, so you see types come in for solving paradoxes or for excluding, discarding some lambda terms, some programs which we do not want to keep because they are not interesting. Okay, so now I will introduce specifically the notion of dependent type. And this is Martin-Löf, as I told you. So here we jump in the 1970s. So a dependent type, I introduce it by examples. So the type sin of n is the type of finite sets of cardinal n. Okay, and well, you may consider that there are many such finite sets. For example, you have a set of 4 apples, of 4 glasses, etc., and they are all equipotent, as we say in logic. So they have the same cardinal, so there is a bijection between them, but still they are different. So can of n phi of n is taking all of them. Okay, so this is the ID of phi of n, and then can of n is some specific way to describe a special, a canonical way, so somehow to describe a set with n elements, namely the set formed by the numbers 0 to n minus 1. Okay, so we suppose that we know the natural numbers, and we take 0, 1, 2, up to n minus 1. So because I started in 0, I stop in n minus 1 so as to have n elements in P. Okay, and I put a little index n here to say that these are the only elements of can of n. Okay, and for example, we can begin to program in with this type can of n, and you have a function that takes a natural number and returns the maximum of can of n plus 1. Okay, so for example, if I take 2, okay, max of 2, no, here we'll take here, okay, max of 2, oh no, max of 2 is going to be the maximum element of can of 3. So it's going to be 2, 3. Okay, and more generally, max of n, okay, max of n is going to be n plus 1. Okay, so if I want to describe the type of max, I will use this type here, which I will introduce more formally later. This is called a pi type. So it's like a function type, okay? Because it's a function, max is a function, okay? It takes a natural number, but the set of in which max of n, the set of which max of n is an element, so the output of max at n is a type that depends on n. Okay, more precisely, the max of n lives in can of n plus 1. So you see that I cannot use just a notation like n arrow a for some a, because if a here depends on n, and this is exactly what the pi type does. Okay, so we will see this type later on. And similarly, we cannot make the product of n. We cannot just make the product of n times can or something like that, because again, can depends on n. So analogously to the fact that we change the arrow into a pi type, we also change the product type into something called sigma type. Okay, and what is this sigma type here? Well, it's a type of pairs formed by a natural number. So this is this component here of our imitation of the notion of product. And the second component will be an element of this type. So it's an element of, sorry, this should be can of n plus 1 here. I will correct this. Well, maybe correct it now, and I will correct this better later. Okay, as an example, if I take the pair formed by 4 and 2, 5, okay, it's an element of this type because 4 is a number and 2, 5 is an element of can of 5. Okay, can of 4 plus 1. Okay, so in this slide, I introduced dependency, pi types, and sigma types. And a more familiar example to programmers, well, that should be more familiar to programmers, is the case of lists. So we can filter lists by the type of their elements. So list of A usually is the type of lists of elements of A. But we can also write a more careful type, which is list of NA, which is a type of lists of elements of A, lists of length n. Okay, and for example, we can see that, well, you probably know how to construct lists. You have the empty list, okay, which is given by nil, and then you have this constructor called cons, which takes an element of A, a list, and produces a new list whose which is obtained by putting this element in front of the list. Okay, so the first element of the list is this new element, and the rest of the list is the old list, which is here. Okay, but now in the dependent setting, you see that nil is a list of length 0. Okay, that's the empty list. So it's an element of list of 0A. And then cons takes a list of an element of A, a list of length n, and returns a list of length n plus 1. Okay, so again, you see the role of dependencies, how dependencies will interact with the programs you want to write. Okay, so as I already suggested, this sigma type is a kind of dependent version of the product type that we have seen in the first slides. And the pi type is a dependent version of the arrow type or function type. Okay, and one way to see this is that you can also see sigma as a kind of disjoint union. Okay, of what? Disjoint union of all bx. Okay, b depends on x. So it's a disjoint copy of all bx where x ranges over a. So when b does not depend on a, this is just a set of disjoint copies of b. Okay, so you should read this as saying that you have cardinal of a, copies of b, and that you take the disjoint union of all these copies. And you know from primary school that a times b is the same thing as b plus b plus b a times, okay, or cardinal a times. And you can do the same analysis for the pi type to see that here you can read this as the product of all the bx when x varies over a. Okay, b depends on x, so it has many. There are many bx's. You take their product, and this is what pi x a b should be. So when b does not depend on a, you just take many copies of b, you make their product, and again you know. Well, this is a bit more advanced mathematics. Maybe this is Lyceum, high school. You know that the exponential is the same thing as taking the product a times, or cardinal of a times. Okay, so now comes homotopy type theory. Homotopy type theory is really starting with this type construction, which was introduced by Martin Löw, who did not anticipate at the time the homotopical nature of this type. So let's not do the homotopy right now. We will do it just after this slide. So let's do things like Martin Löw did them. Okay. So Martin Löw says the following thing: given a type A, given elements x and y of this type, then one can form a new type, which he called the identity type of X and Y, which is more suggestively written also as X equals AY. So the important thing here is that this symbolic representation is a type. This is a type called the equality type between X and Y. Okay, so if you know a bit of logic, this looks like predicate calculus. Okay, the predicate of equality is a formula in logic, and a formula is like a type. We will see this correspondence between formulas and types a little bit later in the course. And so this is, you can think of this expression as an equality predicate. So it's a type. It's a formula, a type. Okay, and then because it's a type, you can ask yourself, does it have elements, terms that have this type? And the answer is yes. If you know that X is actually Y, well, here this equal should be X coincides with Y. Okay, so here we will see these different notions of equality. So when you consider it A of X, you think that this must be true. It must be true that X equals X. So Martin Löw said that there is a term, an explicit term of this type, okay, or a constructor. You know that in programming languages, you have something called inductive types. And usually like natural numbers that can given by zero and successor and other such types. And we will see that the identity type is also an inductive type, which comes with constructors. Actually, it comes with only those constructors which witness that the reflexivity of equality. Okay, so this is the reflexivity. Reflexivity in a relation is to say that X is in relation with X. Okay, so this is why it is called a ref for reflexivity. So Martin Löw assumes the existence of this type. He also assumes that for each X, there is a constructor reflex of type X equals AX. Okay. And let me give you some vocabulary. When a type X equals AY has at least one, there is at least one term of this type, then we say that the type is inhabited. And when this is the case, when the type is inhabited, we say that X and Y are propositionally equal. Okay, good. And now comes homotopy type theory. So far, I just gave you the intuition that this has to do with predicate calculus. But actually, the key insight of Voevodsky, which was anticipated by other researchers, by the way, I mean, before Voevodsky came other people like Streicher and Hoffman, who already predicted somehow the homotopical nature of type theory. But anyway, what is it? What is this homotopical nature, and what is homotopy theory about? Okay, so here is the interpretation. So in order, well, first, before speaking of homotopy, let's speak about interpretation. So in the theory of programming languages, it's important to have mathematical models. So types will be interpreted by some sets, let's say, and programs of some type will be interpreted as elements of these sets. And this mathematical interpretation is quite useful because you can use a lot of tools from mathematics to prove things about programs. So this is why it's important to have interpretation of syntax into some mathematical word. So what is the homotopical interpretation? Well, types will be interpreted as topological spaces. Okay, so a topological space, if you have not followed any course in topology, is, I don't know, it's a circle, it's a ball, it's a sphere, it's a torus, it's a surface or a volume or I don't know. Yes, it's a shape of a set of points together with the notion of continuity in this space. Okay. Now, how do you interpret now an element of a type as a point in this space? How do you interpret proof that two terms are equal? So how do you interpret a statement like P is of type A equals AB? You will interpret it as a path from A to B in this space. Okay, so let's do this. As I said, A is a space. Now, X and Y are of type A, hence they are points in this space. Now, P is prove that X is equal to Y in X is equal to Y. So it's a path in this space. So you see, a path is really a path. So you go from X, you follow a path from X to Y. And Q might be another path. So I have it here. And then what is a term H, which is of type P equals Q? Because in type theory, you can iterate constructions. So P and Q are both elements of the same type, which happens to be an equality type, X equals Y. Then what is an H? Equality of P and Q. What does it look like in this mathematical interpretation? Well, when you have two paths, okay, so maybe I draw it here. If you have two paths, one here and one here, then you have a notion of continuous deformation of the path above to the path below. So you could first, I don't know, do a little thing like this, and then a little thing like this, and then a little, etc., continuously until you arrive to the path below. So this continuous deformation of path P into Q is called homotopy in mathematics. You have a homotopy from P to Q, and graphically, it means that essentially you describe all the space between P and Q, okay? And you describe the gradual transformation from P to Q. So you see that the identity types and their iteration leads you to connections with mathematical homotopy theory, which is all about deformations of paths, deformation of spaces. So homotopy theory is concerned in mathematics with the study of spaces up to deformation. So the idea is that we want in mathematics to be able to say when, I don't know, when this guy here, is it really the same as this guy here? And the answer is probably yes, because both are, I mean, really this, just the curve, the line here, not anything inside. And probably yes, because they all look like a circle. Okay, that's homotopy theory. That you can deform both of them to well, one into the other, or both of them into something more standard like a circle. And probably you cannot do that if between, for example, these two spaces here. So if I have this space on the left and this space on the right, clearly you cannot deform that one into this one, because here you see that you have really two very much separated circles, and no deformation will change the situation. So this is roughly what homotopy theory is about, is to study when spaces can be deformed in one into the other, just like here, when a path can be deformed to another path. Okay, so this is a very, very brief and short introduction to homotopy theory, and the rest of the course will not be really much in the mathematical side. We will do homotopy theory, but only within type theory. Okay, sometimes mathematical intuition coming from homotopy theory will help, but sometimes also purely logical arguments will be even more important to understand what we're doing. Okay, so let me summarize what we've done so far. We have introduced some basic ideas of type theory. So but we didn't do this very formally, and we will never do this formally in this course. This course is mostly about something called informal type theory, which is a way to speak about type theory without being purely formal. Okay, so we have introduced the idea of type and element of this type. So we have introduced this is called a judgment. The judgment that some program A has type capital A. Okay, so you can ask yourself, and a type A, is it an element of some super type? And the answer is yes. There is a type of all types, okay, but not exactly this, okay? So you have a judgment which says that you can collect all types of a certain kind into a big type, the type of types, and you call this a universe, okay? But this universe should not be too big, because this type U cannot belong to U. So you cannot write U column U